welcome back to this NPTEL online certification course in reactive intermediates and the molecular rearrangement. So last couple of class I am trying to solve several problems from the NET, GATE and the JAM exams. So in the today's class I am going to solve some problem from the organosulfur and the silicon chemistry. So the first problem what we can see here, it is started with this particular compound, and you have a OTS group using pH, SNA and DMF. So if you have seen, I think I already discussed, the organosulfur reagents are very good nucleophile, and of course if you have a Na, if you have S minus pH, then that will be even better nucleophile. This is going to take part in a SN2 reaction, so backside attack going to have take part. So that is going to generate you the corresponding product where you can write SPH. So this will be the corresponding product. If you see among this option, this cannot be the correct answer. So this is going to be the correct option here, the option B. So the option B is the correct option here. So let's move to the next problem here. The major product formed in the following reaction is. So what is going to happen if you start with this compound and treat with B4NF, tetrabutyl ammonium fluoride. So if you use it, if you use the TBAF, then what is going to happen here? If you remember, we talk about that the F minus going to react with attack to the silicon through a pentavalent. It will form a pentavalent compound at the beginning, and then that will allow cleavage of the carbon silicon bond to generate a corresponding carbon ion, and now you have a leaving group here, NMe3 plus. What is going to happen? This can dearomatize the ring, get rid of this NMe3, generate this generate this some sort of a diene species are here. Of course, we can see a diene here with 2 methyl group in the terminal position, a symmetrical one. Now if you react it with this so you can see this is a diene and this is clearly a dienophile. Once you have a dienophile, it will going to take part in a 4+2 cycloaddition. So it will be take part in a 4+2 cycloaddition, and if it is a 4+2, what is going to be the product? Instead of writing that, I can first write the I think you can write this way. So you will have a 6-member ring here, and if they are facing in the same side, this methyl, they are approaching the same phase. So they are trans to each other. These 2 ester group are trans to each other, so that will be also reflect in the product. So this is going to be your answer here. Now if you look into all the different answer, here I think this has to be correct. Here that is not correct. Here also that is not correct. And here they put both the ester on the same side, but we started with the trans. So this is going to be the right answer, the option A. So going to the next problem here, what will be the, I think we talk about, this is a very important reaction. Once you have this the SPH group, if you remember, we treat with MCPBA. What is going to happen? It is going to oxidize to the corresponding sulfide to a sulfoxide. So you will get a SOPH. Now it treated with acetic anhydride. So it can, I think if you remember the Pumera arrangement I talk about in the class. So once you have this, let me not going to take care of everything. I am just going to draw this much. For simplifying the problem, you have so we can write SO as a, if you remember, S plus O minus, I already discussed in the class, that the sulfur oxygen have a oxygen is more electronegative, it can take the electron density towards the oxygen. So, you will see more electron density on the oxygen, and now you have acetic anhydride ACTO, which will be nothing but a CH3 COO COCH3. So, this O minus can attack here, get rid of this an acetate minus to form. I am not drawing the entire part, that is why I am writing like that. So, I hope you have no problem with that. Again, I think sulfur is a plus, and this can now allow you, and you have this the OAC minus, which can come back, take this proton and allow you get rid of the OAC to generate some sort of a thiol species. Okay. And again you have acetic anhydride in the medium, so that means you have acetate. This can attack here. And if you remember, once you have this species, it can there will be a protonation plus another acetate, and I think you are going for aqueous sodium carbonate. So, the water can attack here to take you to some species like this, and that can finally form the corresponding diketo compound. So, you end up forming a corresponding 1,2 dicarbon compound. So, if you look into all the, so you can see here the product will be 1,2 dicarbon compound. This is not the correct option, B is not correct, C is not correct, the D is the correct option, because you can see there is 2 different carbon compound, there is 1,2 dicarbon compound. Okay. So, this is I think I already told about, I think this the Pumera rearrangement in the class I talk about the mechanism. So, please practice, you will be expecting more problems in the exam. So, what will be the major product formed in the following reaction? If you have remember, we talk about this reaction, that once you have this if you remember the starting material for this reaction, this is the Peterson olefination problem. So, clearly if you understand that this is started forming by the reaction of a carbon ion from alpha to the sulfur, alpha to the silicon with a reaction with the corresponding aldehyde, correct. That reaction actually generate this silanol, and once you have this, you treat it with H2SO4 and TVAP. So, what is going to happen if you treat with H2SO4 in this compound? So, I talk about the beta effect of silicon. Remember, I think if you forgot, then you should definitely go back. So, they are trans. So, you have a CH2 and then OTBDMS. So, now you have a H2SO4 that can protonate this, as well as you have a sigma bond between carbon oxygen that will have a sigma star orbital here. So, this can get electron density from the carbon silicon sigma. So, carbon silicon sigma bond, electron density to the carbon oxygen sigma star orbital. So, this can make the carbon silicon bond weaker. So, you can the H2O now can attack here, silicon forms a double bond between the carbon and get rid of the water. So, that will allow you through anti-elimination happening here, that can allow you to generate a double bond which is trans. Now, you have this OTBDMS and you treat it with TVAP. Okay. So, again this is a tarbutyl dimethylsilane. So, you have a silicon which is having a dimethyl and a tarbutyl group here. Okay. So, you with oxygen. So, that is the OTBDMS. I am telling this several classes. So, what is going to happen? You have a F minus going to attack here. Again you can see is formation of a pentavalent silicon, and then there will be cleavage of the silicon oxygen bond to end up generating the corresponding alcohol. Okay. So, you will be generating corresponding allylic alcohol here. Okay. So let's look into all the options. Your TBDMS cannot be survived, so option A is not correct. Option B is correct because you can see the allylic alcohol is forming. Neither C or D is correct. So the B is the correct option. So let's go to the next problem here. So what we are seeing, they are asking, you have this allylic alcohol, you treat with the COCl(2) or the oxyl chloride and DMSO. So if you remember, with activated DMSO, we are talking about a oxidation reaction of the allylic alcohol. But what you have oxyl chloride and DMSO. If you remember some reaction at -60 degrees, that is Swan oxidation. I already discussed in the class. So if you remember, in Swan oxidation, we can consider DMSO as a plus and minus. So this can react with oxyl chloride. Okay. So what is going to happen here? This O minus can attack here. This will come back, get rid of Cl. Correct? And your sulfur has a positive charge here. Then what is going to happen? You have a Cl minus which can attack here. Then you will be forming a CO2 and a CO. So what you are getting out? You are getting out minus CO2 minus CO to generate this activated species. Okay, this sulfonium is going to react with your alcohol here. That is the next step of this reaction. So alcohol is coming and attacking, getting rid of the chloride. But the problem happened that after that, the next step, if you remember the mechanism, the next step, your base has to come and deprotonate to form the ylite. That can able to abstract the alpha to the alcohol proton and form the corresponding the aldehyde. But because you don't have that, now this become an activating agent and you have a Cl minus in the medium, this can come and go for a SN2 reaction. So instead of going for a alcohol oxidation, you will end up generating a corresponding allylic alcohol, allylic chloride. So you generate corresponding allylic chloride as a product. So now if you look into this, cannot be the answer, neither the B or C, so the D is going to be the correct option here. So if you remember, if you don't have a base in the Swan oxidation, you end up generating corresponding allyl chloride. So what will be the product in this reaction? First thing, you use this alkyl halide, you use triphenylphosphine. So if you use triphenylphosphine alkyl chloride, you remember these are very good nucleophile, they can go for a SN2 reaction to form this compound called triphenyl plus Br minus. Use sodium hydride, so they can able to abstract this acidic proton to generate a ylite, phosphorus ylite. And now you are taking this ylite and reacting with a benzaldehyde. So if you remember in this reaction, what is going to happen? It is going to generate a olefin here. And again, these are a unstabilized ylite. If you react with the unstabilized ylite, then you end up generating this compound here. Okay, I think I already talked about this. This mechanism of this, because if you remember, you have ylite, then it will come and form some sort of a bond like this. You have phosphorus oxygen bond. Correct. And then that is going to, you'll able to form a double bond and a triphenyl phosphine oxide as a byproduct. So this can form the oxaphosphatine intermediate and form, it will cleave it and going to go to the, so now once you get here, so that's why you end up forming a Z olefin. As if you remember, a unstabilized phosphorus ylite react with the corresponding aldehyde to form a corresponding Z olefin. So you end up a G for olefin, you have a OH here, you have a base in the medium, so this can able to go for a SN2 reaction that will generate you to this product. Okay. So now if you look into all the different answer, this cannot be correct, neither B or C, the D is going to be the correct option here. So first there is a there is a Wittig olefination, and then there is a internal cyclization through a SN2 reaction of oxygen. So moving to the next problem, what we are learning here in this reaction, you have alpha beta unsaturated carbonyl compound, you are treating with this trimethyl sulfox. So you have a you have a sulfoxide here, and then you have a sodium hydride, so that can able to generate the sulfoxonium. If you remember, I talked about in the previous class, this will generate a stabilized sulfoxonium ylide. You have a sodium hydride, this condition can generate this corresponding sulfoxonium ylide, which is a stabilized ylide. So stabilized ylide will go for a 1,4 addition. That means this CH2 minus can go for a 1,4 addition here. Okay. What is going to happen if it go for 1,4 addition? We will come back to the stereochemistry in a minute. CH2 and then SO plus, this will come back and going to take react here, get rid of this. Of course you have to remember that there is a methyl group here. Okay. So this will try to avoid the steric to generate a product like this. There is a cyclopropane going to form, but in the opposite phase. Okay. And then we can clearly explain this this type of reactivity from this tangent state. So you can think about this is the corresponding carbonyl. Now you have the methyl group, which is in this position. Let me see, the methyl group is one carbon part, so you can have a methyl group here, 3 hydrogen of the methyl group. It could be above or below. So if you have a methyl group below, then so I have drawn above, let me draw it below according to the stereochemistry here. So I think it is fine whatever I am doing. I am just trying to explain you. If you have a methyl group in this phase, then the cyclopropane, then the nucleophile the approaching of this the sulfoxonium ylide cannot happen this phase due to steric. So it is have to happen from the opposite phase. Okay. That means the corresponding cyclopropane going to form from the other phase. That means you will be end up forming this particular product, not the other one where the cyclopropane is in the same side of the methyl. So we got that answer. Now if you look into all the different answers, this one seems correct, neither this one, okay, not this one either. So now if you look into the next answer, what is going to happen? You give single electron, the reduction reagent, the lithium and liquid ammonia. Lithium and liquid ammonia do the ring, rupturing of the cyclopropane, so that they can do the ring rupturing of cyclopropane to generate a methyl group here. So you will be forming a carbonyl group that is going to cleave the cyclopropane to form this compound. Again, whatever mechanism this is happening, this can happen either through this first, the reduction of the carbonyl forming a O dot, okay, formation of O minus and a C dot that can come back here and form a radical, form a CH2 dot here, and that can take another electron to make a CH3, and then finally this can come back to the corresponding carbonyl. So that way it will end up forming this product. Okay, the next problem here, you have alcohol here, you have a secondary alcohol, you treated with iodine and PPH3 with a base. If you remember this reaction I covered in the class, it is the Appel reaction. So what is happening here? You have alcohol, so you have a PPH3 with I2. So PPH3 can react with I2 to form PPH3 I plus and I minus. This I minus can able to take this proton to form O minus, and that can attack here, get rid of this to form this OPPH3 plus. Now you have I minus, come back, attack here and get to the corresponding. So you will be replacing this alcohol by iodo. And now once you treat with, so you have this corresponding zinc reagent, and then you are using zinc, palladium source, and you have a corresponding aryl bromide. The zinc can able to make corresponding zinc iodide here, and now it can able to go for a Negishi coupling. You have aryl bromide and you have a palladium source. I think I already discussed this in the class, that this can go for a Negishi coupling to include this corresponding bromide will be replaced here. So you will be end up forming a product where one aryl ring will be introduced here, okay, where you will have a cyano and then you have a chlorine here. So if you look into all the options, this is the correct option in every cases. So answer option A and B have a correct option for A, but here only in case of B you see the correct option, because the cyano will be in the next to that bromo. So this is nothing but Apple reaction and a Negishi coupling to get to the corresponding product. So here what is the major product in this reaction? Again you are using a KH and you have a silicon and you have a OH, okay. They are in the vicinal carbon. So what is going to happen? The KH become corresponding O minus, form oxygen silicon bond, then they are going to take part in a scene elimination going to happen. I think if you remember in the Peterson olefination there is a scene versus anti, and this is going to go for a scene elimination, and that will end up forming the corresponding olefin. So you will be able to form this corresponding olefin from there. Means you have a double bond here, you will have a OH and you have a O benzyl. Now you treat with MCPBA. What is going to happen? MCPBA going to go for, if you have a olefin here, it is going to go for epoxidation. Now you have a OH group here which can act as a directing group. Remember, directing group epoxidation. That means the epoxide will be forming in the same side. So let's go to the this particular problem here. So here we are talking about again a reaction of you have a indole, you have DMF and POCl3. So what are you going to product? So I think this is a very important reaction I talked in the class, is a Vilsmeier-Haag reaction. So in the Vilsmeier-Haag reaction, what is the reactive intermediate? Let me try to go through the mechanism again. You have this NN dimethyl and you have this POCl3, correct? So what is going to happen? You can think about this reacting to the oxygen, getting rid of the chlorine, formation of this iminium species with OPOCl2, and then you have a minus Cl minus which is going to come back and attack here, and this is going to generate your with a chlorine and with a OPOCl2. So this is getting a better leaving group. So this nitrogen lone pair going to come back, get rid of this, and it is going to generate. So this is the reactive intermediate in the Vilsmeier-Haag reaction. Now if you have a electron rich species like indole, which can react, which can track electrophile at the C3 position, so they can come and attack here to neutralize the charge on the nitrogen. Let me draw that. Okay, it is going to form this species, and you can see there is a plus on the nitrogen. Now this proton will be started to form. So indole will come back, and now you have a chlorine. So, nitrogen lone pair can give electron density to get rid of Cl, that can form the corresponding iminium, which once is going to hydrolyze. So, corresponding N corresponding iminium can be hydrolyzed to the corresponding aldehyde. So, you end up generating this corresponding aldehyde in the C3 position. Okay. So, please practice the Bills-Meyer-Haag reaction. It can be there are multiple problem comes in the exam using the Bills-Meyer-Haag reaction. So, once you have this active intermediate, it is now going to take part in Friedel-Crafts type reaction to get to the corresponding product. So, this will be the correct option A, not the B or C or D. Okay. So, again thank you so much. I think this is the answer here. You can see. Again, thank you so much for coming to the class, and I hope you have enjoyed the problems in the sulfur and the silicon chemistry, and I am going to see you guys in the next class. Thank you.